the last section for Unit 6, which we talk about direct, inverse, and joint variation. So direct, inverse, and joint are different variation models. So direct variation is a direct relationship is when the variables are both increasing. So as x increases, y increases, or they're both decreasing there. As x decreases, y also decreases. Y equals k times x. K cannot equal 0. So this is your standard direct variation equation, which might look familiar. K is called the constant of variation. A direct variation is a linear relationship because it changes at a constant rate. Here's an example. The math club is selling t-shirts for $10. The table shows the number of shirts purchased and the total cost. So as the number of shirts increases, 0 shirts, $0. 1 shirt, $10. 2 shirts, $20. 3 shirts, $30. So as the number of shirts increase, so does the cost. And it's changing by $10, so that's your constant of variation. So this would have an equation of y equals 10x, $10 per shirt. So that's a simple example of a direct relationship or something that has direct variation. And so in this one, your constant of variation, your k, would be 10. Sometimes we call that our slope in a linear problem. But for direct variation, it does have to have a y-intercept of 0. 0. Inverse variation is the reverse of that. So as x increases, y is decreasing. Or as x decreases, y is increasing. K is still considered the constant of variation, and it reads as y varies inversely with x. Here's the equation. So it's with division instead of multiplication. So it'd be y equals k divided by x. So for example, the choir fundraiser, Billy can afford 15 tickets that are $5 each. How many tickets can Billy buy if they're $3 each? Well, if he can afford 15 tickets that are $5 each, 15 times 5 means he has $75. So how many tickets can he buy if they're $3 each? Well, that's 75 divided by 3 would tell me how many tickets he could buy. So this time your constant of variation is the $75 that he has, and the price of the ticket is the X. So it could be if he has $5, he could buy 15 tickets. If the tickets are $3, he can buy 25 tickets. So as the price of the ticket goes up, the number of tickets he can buy goes down. As the price of the ticket goes down, the number of tickets he can buy goes up, because here he can buy 25 tickets. So the price is lower, buy more tickets. So as one increases, the other decreases, or as one decreases, the other increases. So that's inverse variation. Inverse variation can also be written as x times y equals k, because if you have y equals k divided by x and you multiply both sides by x, then you get the x times y equals k. And we're going to use that idea a lot to solve for k for inverse variation. So just identifying it, do x and y show direct variation, inverse variation, or neither? So solve for y essentially. So in A, y would equal 4.8 divided by x, which means that that is inverse variation. Here, I'd have to solve for y. I'd have to multiply both sides by 1.5. So y would equal 1.5x. And 1.5 times x means as x increases, so would y. So this is direct variation. If I say x and y vary inversely, that means that inversely, so y is inversely related with x. If y equals 6 and x equals 1.5, write the equation that relates x and y. So then I'm going to plug in 6 for y and 1.5 for x. And then I need to solve for my k, my constant of variation. So if I multiply both sides by 1.5, 15 times 6 be 9. Add back in my decimal. So I'm going to get k equals 9. So that's my constant of variation. So for the equation, it would be y equals 9 over x. That's your constant of variation. So when x equals 6 and y equals 1.5, the equation that relates x and y would be y equals 9 over x. Then use that equation to find y when x equals 4/3. So now it just wants me to use the equation to plug in 4/3 for x. So here you're going to have to multiply by the reciprocal because you're dividing by a fraction. So 9 over 1 times 3 over 24, or 3 over 4 is 27 over 4. Okay, you might see something like this. The volume in a gas container varies inversely with the amount of pressure. A gas has a volume of 75 cubic inches at a pressure of 25 pounds per square inch. Write a model that relating volume and pressure. So first it's inversely. So typically it's inversely is constant of variation divided by x equals y. Now this is a gas. Volume in a gas container varies inversely with the amount of pressure. So the volume varies inversely with pressure. So it'd be V equals K over P. So volume varies inversely with pressure. Then it says that the volume is 75 cubic inches. So I'm going to plug in 75 for volume. And the pressure is 25 pounds per square inch. So I'm going to plug in 25 for pounds. Then I can use that to solve for your constant of variation in this problem by multiplying both sides by 25. So 75 times 25 is going to be 1,875. That's your constant of variation, which means your formula then for volume will be 1,875 divided by pressure. So that's the model that relates volume and pressure. Okay, if I give you a table and says, does this data show inverse variation? So let's say that this is x and this is y. So if it varies inversely, it would be like y equals k over x, or k would equal x times y. So basically, if we multiply these two columns, like w times h, does it equal the same thing each time? So like 2 times 9 is 18, so that 3 times 6 is 18. 10 times 1.8 is 18. Oops. So those work. I know just by looking at it. 4.5 times 4 would be 20. That's 18 too. And I'm guessing this one would be 18 too. So that means that they do vary inversely, which means that you could get your W. This one, the W is smaller. So it would be H is equal to 18 divided by W. So 18 divided by 2 is 9. 18 divided by 4 is 4.5. 18 divided by 6 is 3. So it does show inverse variation. If it was direct variation, that one starts as y equals k times x. So then you would say that you would look at your y's divided by your x's, and that's how you solve for k. So take all the y values divided by x's instead of x times y and see if that equals the same value of k. If so in your table, then that is direct variation. And whatever you got when you took y divided by x, that's your constant of variation. Joint variation is the last type of variation we're going to look at. This is when a quantity varies directly as the product of two or more other quantities. So like z equals k times x times y. So k can't be 0 because that's your constant of variation. So we would say that z varies jointly with x and y. This might be an example. The amount of wear and tear on a book varies jointly with the type of paper it is printed on and the amount of use it has. So, you know, x and y being the type of paper and the amount of use, that together with your constant of variation will tell you how worn out the book is. So they are going together. If I say write a joint variation model and I give you an x, y, and z, I want you to solve for the constant of variation and then use that to write the model. So first you start with, you know that z equals k times x times y. Plug in what was given. So k times negative 4 times 5. So that's 60 equals negative 4 times 5 is 20. So solve by k by dividing by negative 20, you're going to get negative 3. So your constant of variation for these three data sets is negative 3. So a model that would work would be z equals negative 3xy. So you solve for your constant of variation, you plug it back into the model. Then use the model to find another point in the set. So I have find z when x equals 7 and y equals 2. So plugging in 7 and 2. So that's negative 21 times 2 would be negative 42. You can do multiplication in any order there. So, all right, let's just practice writing a few equations with the different wording. Y varies inversely with x cubed. Inversely implies that one's increasing, the other's decreasing. So that's division. So y varies inversely, so that's k over x cubed with x cubed. Directly with x, y varies directly with x and inversely with z squared. So directly means they're both increasing. Inversely means one's increasing, the other's decreasing. So y varies directly with x, so k times x, but inversely with z squared, so divided by z squared. Z varies jointly with x squared and y. So jointly is a string of multiplication. So x squared times y, x squared y. Y varies inversely with x and z. So y is inversely means division with both x and z. Y varies directly with x squared but inversely with z. So that would be directly with x squared would just be like this. And then inversely with z would be divided by z. Okay, we have one last example here. The ideal gas law states that volume in liters varies directly with the number of molecules and temperature and varies inversely with pressure. The constant of variation denoted by R is called the universal gas constant. So write an equation for the ideal gas law. So first, V varies directly with the number of molecules N. So that would be V varies directly with N. And remember the constant of variation is R. So that's usually our K, but this time it's R. So Rn. Oh, it varies directly with N and T. So N and T. And then it varies inversely with pressure P. So inversely with P. And then remember that R is really like our K. That's our constant of variation. But this one has a special variable for it. So that's the model. Now it says to estimate the universal gas constant if the volume is 25 or 251.6 plugged in for V. N is 1, T is 288, and P is 9.5. So essentially I get 288R over 9.5. So I'm going to multiply both sides by 9.5. I need a calculator for this, but let's see. 0.2 equals 288R. Then divide both sides by 288. BR is approximately equal to 8.3. I didn't put the units in here, so we had moles times kelvins divided by I'm not sure what the units would be. I'll have to look into it more. There we go. The R, the universal gas constant, is 8.3. So there's a nice review laid out for you too.